Hello students. So in the previous video, we took the properties of a LTI system in terms of impulse response. In that, the first topic was system interconnection. That means we explained how, that means we discussed about how the system can be expressed when the LTI system is connected in parallel as well as cascaded, and they possess how they possess the properties of LTI system. When the system is connected in parallel, the system possesses distributive property. When the system is connected in cascade, it possesses both associative property and commutative property. So that is the proof we have discussed in the last video. Now moving on to the next topic. So these are the properties of LTI system continued, and here we have 4 properties. So first one is memoryless, second one is causality, stability, and so these are the 4 properties that we are going to discuss: memoryless, causality, stability, and invertibility. So why only 4? If you go through the properties of systems, we have memory, causality, stability, invertibility, linearity, and time invariance. Since these properties that we are discussing is only about LTI system, so that means the system already possess the 2 properties, that is linearity and time invariance. So all the system will possess those properties. So excluding those 2, we remain with the 4 properties. So those are memory, causality, stability, and invertibility. Okay. Now these properties are expressed in terms of impulse response only. Okay, so that means we have to consider an LTI system which possesses an impulse response. So let's start with memory. So here you should remember this diagram whenever you are dealing with an LTI system. Okay, so this is an LTI system. So input is x of n and output you will get y of n. So that's for sure. And this will be a convolution of x of n and h of n. So that is the output of the system. So you have to remember this whenever you are going through the properties of LTI system. So first one is memory, or it is also called as memoryless. So that doesn't change the property of this. You can call this a system with memory or system without memory. So what is the definition of the system? So the property says that so we have to derive this for both the discrete time and continuous time LTI system. So let's take the definition of it. A discrete time LTI system is said to be memoryless if and only if its impulse response is of the form h of n is equal to c into delta n. So that means we will be checking the system's memory, whether the system is memory or not, based on its impulse response. And the impulse response should be of this form, then only the system is said to be memory less. Okay. So this is for a discrete time system. Similarly, for a continuous time LTI system, so the condition will be the system is said to be memoryless if the impulse response is of this form, that is h of t is equal to c into delta t. So this is the condition in case of continuous time, and this is the condition for a discrete time LTI system to possess memoryless. Okay. So if it doesn't satisfy this condition, then the system is said to be memory. So that is the definition of the property memory here. So moving on to the next one. So we'll take examples on this and verify all the properties once in for each system. So that's why I'm not taking any example here for each property. We'll take all at once. So next is causality. So what does it say? A LTI system is causal if and only if its impulse response satisfies the condition. So first I'll write for discrete time. H of n is equal to 0 for n less than 0. So this is the condition here. This is what we have to remember. So the impulse response should be 0 for values of n which are less than 0. So this is for discrete time. Similarly, for continuous time, LTI system, the condition goes like this. The impulse response h of t should be 0 for value of t less than 0 because t represents time index. In this case, n represents time index. In this case, t represents time index for continuous time system. So for negative values of t, h of t should be 0 for the system to be possessing causality property. Okay. So next is stability. So this definition goes like this for stability. A LTI system is bounded input, bounded output. I am writing in short, bounded input, bounded output, stable if and only if its impulse response is absolutely summable. So this one is for a discrete time system. The meaning of this is the impulse response. Here you can take write down this impulse response here. I'm taking discrete time. So impulse response is absolutely summable. So here the limit k varies from minus infinity to plus infinity. So this should be less than infinity. The condition is the system is said to be bounded input, bounded output stable if and only if the impulse response of the system is absolutely summable. Since it's discrete time system, we take the summation here, so that's why it end with absolutely summable for a discrete time system. So if you apply h of n and if you apply the limit here for the summation, so the value of that should be less than infinity. So the input should be a bounded input, and then only you can get a bounded output. So bounded input means an input which having value that is less than infinity. So some finite values. So that is called a bounded input. So if you give that kind of input to the system, so then you can expect a bounded output. So bounded output means the output should also result in a finite value that should be less than infinity. So then only the system is said to be stable. And here we have used modulus, or you can take the consider it as magnitude or modulus, whichever suits for you. That means it should only produce positive values. Okay, so that value should be less than infinity. So in case of continuous time system, similarly, for a continuous time LTI system is bounded input, bounded output stable if and only if its impulse response. So in case of a continuous time system, the impulse response is h of t, and only if its impulse response h of t is absolutely integrable. So in case of continuous time system, so the impulse response should be absolutely integrable. Then only we say that the system is stable. So if you express that mathematically, it says the integral tau varying from minus infinity to plus infinity modulus of h of tau d tau. This value should be less than infinity. So the integration of the impulse response should produce a finite value which is less than infinity. Then only the system is said to be stable. So this is the difference between continuous time and a discrete time LTI system to possess stability property. Okay. So finally, moving on to the last one, that is invertibility. Okay. So let's take the discrete time here. A discrete time LTI system with impulse response h of n is said to be invertible if and only if the condition goes like this, if and only if h of n is equal h of n convolved with h inverse of n should be equal to a delta n. That means h of n and its inverse or convolved, so it should end up with a value that should be impulse response. Then only the system is said to be invertible. So if you express this in graphically, so this is a system, the first system x of n, so the output will be y1 of n. Then the output of this system is passed through an inverse system, then you will get the output y of n here. So that means here the output should be equal to delta n. So if that happens, then the system is said to be invertible, because if you say y of n is can be written as the convolution of y1 of n and h inverse of n. And what is y1 of n? It is the convolution of x of n and h of n. So these two are convolved with h inverse of n here. So as per the associative property, we can write this in this way, that is x of n whole convolved with h of n and h inverse of n. So therefore you will get x of n convolved with delta n. Why means, because the property says if it is invertible, then you will get x of n convolved with delta n. So then the output, at the output we can recover our input, because the property says x of n convolved with delta n is equal to x of n only. Okay, so here I think I should have written x of n, because that is the input which we have to recover from the output. So if the input can be recovered from the output, then the system is said to be invertible. So to make this happen, then the impulse response should be of this form, that is h of n and h inverse of n should produce delta n. So if these two produce delta n, then only we can recover our input from the output y of n. So that is the overall explanation of the invertibility property. Now if we express the same for similarly for continuous time, LTI system, the condition will be h of t convolved with h inverse of t should be producing delta t. So the convolution of these two, if these two produce impulse function, then only we can recover the input from the output of the system. So that means the system will possess invertibility property here. Okay, so these are the four properties. Now we take some examples on this, and let's verify whether the system possess these properties or not. Okay, so let's start with some examples on this. So we'll take the first one. So the problem is like this: check whether given LTI system with impulse response h of n is equal to 2 to the power of n u of n minus 1 possess the following properties. So what are the properties here? We have to check. First one is stability. Second one is causality. and third one is memoryless. Okay, so these are the properties we have to verify, and the system is having an impulse response h of n is equal to 2 to the power of n u of n minus 1. So let's take one by one. First, we'll start with stability property. So the definition of stability is, since it is a discrete time system, if the impulse response is absolutely summable, then only the system is said to be stable. Here, in this, let's mention this S, which represents stability for both the case. Okay, so this will be easier for us. S represents stability property that we are verifying, and I will use the same here. So the condition goes like this: summation k is equal to minus infinity to plus infinity h of k. So this value should be less than infinity. Okay, so let's verify whether it is having that property or not. So k is equal to minus infinity to plus infinity. So what is h of k? So we have to express h of n in terms of h of k. So that's it. And so just replace n by k, you will get the value for h of k. So it is 2 to the power of k u of k minus 1. Okay. So now the limit is varying from minus infinity to plus infinity. If you observe, we have u of k minus 1, which is a unit step function. Now the value of unit step function is 1 for certain duration. Now what is that duration? Let's check out. So call this as 1 here. So u of k, I am expressing unit step function in terms of k now, because here we have u of k minus 1. So same, from the definition of that, we can write that u of k is equal to 1 for k greater than or equal to 0, and u of k is equal to 0 for k less than 0. So this is from the definition of unit step function. So what we want here, we want a limit for u of k minus 1. So that means u of k minus 1 is equal to 1 for k minus 1 greater than or equal to 0, and it is 0 for k minus 1 less than 0. Now if you further simplify, move this k here, 1 here, so k greater than or equal to 1, and this gives you k less than 1. So this is the limit that we have here. So what does it say? U of k minus 1 is 1 for values of k which are greater than or equal to 1, and u of k minus 1 will be 0 for values of k less than 1. So that is the meaning of this. So let's apply this limit and make u of k minus 1 as k minus 1 is equal to 1. So therefore, S is equal to summation k is equal to, since u of k minus 1 will be 1 for the limit k way greater than or equal to 1. So the limit changes from 1 to infinity, 2 to the power of k into 1. So this gives us k is equal to 1 to infinity 2 to the power of k. Okay. Now here, if it is possible for us to bring it to by applying geometric series to bring it to a reduced version, we can apply that. If it is not possible, so just observe this here, the limit k is varying from 1 to infinity. So if you expand this by applying values for k, you will get like 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3 plus 2 to the power of 4, and it will go all the way to 2 to the power of infinity. So that means if you expand this expression, that summation, So you won't get a finite value because it goes all the way to infinity, and 2 to the power of infinity is infinity only. So anything added with infinity, you will get an infinite value. So that means the impulse response is not absolutely summable. So therefore, the system is not stable. Okay, so we have to conclude like this. Since impulse response h of n is not summable, comma, the system is not stable. So this is how we conclude with the justification. So h of n is not summable, therefore the system is not stable. Or you can express this mathematically, that k varying from minus infinity to plus infinity, h of k is not satisfying this condition, therefore it is not stable. Okay, so this is stability property. So the next one is causality property. So the causality property says that if the system is said to be causal if its impulse response h of n should be 0 for values of n less than 0. Okay. So given our impulse response h of n is equal to 2 to the power of n u of n minus 1. Now let's apply some values for n which are less than 0. That means we have to apply some negative values. So for n is equal to minus 1. So what we get, h of minus 1 is equal to 2 to the power of minus 1 u of minus 1 minus 1. So 2 inverse can be written as 1 by 2. So here you will get u of 2. 1 by 2 into u of minus 2. So from the definition of unit step function, it says it is present only for values of n greater than or equal to 0, and it will be 0 for values of n which are less than 0. So that means u of minus 2 is a negative value, which means it is 0. So that gives us 1 by 2 into 0, that is equal to 0. So that means the impulse response h of n is 0 for value of n less than 0. So that means the system is satisfying the condition of causality. So therefore we can write it, the system is causal. Okay. So the third one is memoryless. So the condition for a system to be memoryless is the impulse response of the system should be of this form, that is C into delta n. If the impulse response is of this form, then only the system is said to be memoryless. And here C is nothing but a constant value or an arbitrary function. So it is just, it possesses some integer values. Okay, not necessary that it should be an integer, it will be a constant value. Okay, so that means if you compare the given impulse response given h of n is equal to 2 to the power of n u of n minus 1. Now if you compare this with this, so this c, okay, you can take in place of c we have 2 to the power of n, which is not a constant, but delta n is not there, we have only u of n minus 1 here. Now comparing this with this expression, so the equation is not satisfied. So therefore, the condition is not satisfied for memoryless. We can say that the system is not a memoryless system. How to conclude this? We can conclude like this: since h of n is not in the form h of n is equal to c into delta n. Since h of n is not in the form of this, therefore the system is not memoryless, or you can write it as the system possess memory. Both suits better. Whichever you find comfortable, you can go with this. That is, system is not memoryless, or you can conclude like the system possess memory. Okay, so we verified all three properties for the given system with impulse response h of n is equal to 2 to the power of n u of n minus 1. So the given system possess is not stable, but it is causal and it is not memoryless. So this is the conclusion for the system. So let's take one more example for the different, we take a different kind of system here, which will be okay. So here is a problem given: check whether the given LTI system is stable, causal and memoryless with impulse response h of t is equal to e to the power of t u of minus 1 minus t. Okay. So now let's check the properties for this. So well, first we take stability here. Forgot to mention this. So this is a solution for this. So first we check for stability. So what is given? H of t is equal to e to the power of t u of minus 1 minus t. Okay. Now, what is the condition for a system to be stable? So the says that the system is said to be stable if its impulse response is absolutely integrable. So based on that, this is h of tau. So this is the condition it should satisfy. Okay. So now let's substitute the value of h of tau. So tau is equal to minus infinity to plus infinity. H of tau is given. So express this in terms of tau, e to the power of tau, u of minus 1 minus tau d tau. I think I forgot mentioning d tau here. So d tau, so this is the condition. Here we have u of minus 1 minus tau. Let's take the limit from which value it is 1. So u of tau is equal to 1 for tau greater than or equal to 0, and u of tau is equal to 0 for tau less than 0. Now given is u of minus 1 minus tau. So we want the limit for this. So u of minus 1 minus tau is 1 for minus 1 minus tau less greater than or equal to 0, and it will be 0 for minus 1 minus tau less than 0. Now if you simplify this, so we have minus 1 minus tau greater than or equal to 0. So minus tau is greater than or equal to 1. So tau is equal to greater than or equal to minus 1. Okay. Next, here minus 1 minus tau less than 0. Minus tau is, I think I made a mistake here. So if you multiply by minus, it will become less than or equal to, so less than 1. So multiply by minus, tau greater than minus 1. Okay. So this is the meaning of that. So these are the new limits. So let's substitute here. So this gives us tau less than or equal to minus 1, and this gives tau greater than minus 1. So these are the new limits. Now u of minus 1 minus tau will be 1 for values of tau which are less than or equal to minus 1, and for values of tau which are greater than minus 1, u of minus 1 minus tau will be 0. So this is the meaning of this. So let's take this new limit here. If you observe this, the limit now it is varying from minus infinity to plus infinity. Just for simplicity, give a equation number for this. Now tau, for tau less than or equal to minus 1, u of minus 1 minus tau will be 1. So that means our limit varies from minus infinity to minus 1. Okay. After the values above greater than minus 1, u of minus 1 minus tau will be 0. So that means our limit will be from minus infinity to minus 1. So in this duration, u of minus tau minus 1 minus tau will be 1. So then what happens to the equation? E of tau into 1 d tau. Okay. Now if you integrate this, e to the power of tau, integration of that, e to the power of tau, and limit are minus 1 and minus infinity. Okay. So e to the power of minus infinity is 1. So you will remain with, if you apply the limit, so e to the power of upper limit is minus 1 minus e to the power of minus infinity. So e to the power of minus infinity is 0. Okay. Next, will only remain with e to the power of minus 1. So this will give you a finite value. If you can check that e to the power of minus 1, you will end up with a finite value which will be less than infinity. So that means our impulse response is giving a, if you integrate that, our impulse response will produce a finite value which is less than infinity. So that means the system is stable. So you can conclude like this, or you can just simply, you have mentioned this condition here. So therefore the system is stable. Or you can elaborate by saying, since the impulse response is finite, or impulse response h of tau, the integral of that is less than infinity, this condition, okay, is less than infinity, therefore the system is stable. So it's up to you. Okay. Next one is causality. So condition for a continuous time system to be causal is h of t must be 0 for t less than 0. So apply, what is the impulse response given? It is e to the power of t u of minus 1 minus t. Okay. So let's apply some negative values. So first I will put t is equal to -1. So what happens to this? H of -1 is equal to e to the power of -1 u of -1 minus of -1. Okay. So e to the power of -1 u of, this is -1 and minus of -1 will be +1. -1 plus 1 will become 0. And u to the power of 0 is 1 from the definition. U of n is u of t, right? U of t is equal to 1 for t greater than or equal to 0, and it is 0 for t less than 0. So let me write it clearly. So this is u of t. So that means you will end up with e to the power of inverse, which is a finite value. So that means h of 1 is, sorry, h of -1 is giving a value. That means the condition is not satisfied, that the impulse response h of t should be 0 for negative values of t. But if you apply negative value for t, this h of t is not becoming 0, it is giving some finite value here. So therefore h of t is not equal to 0. H of t is not equal to 0 for t less than 0. So that means the system is not causal. Okay. So the third one is memoryless. So third one is memoryless. Now the condition for a system to be memoryless is its impulse response should be of the form c into delta t. So if this condition is satisfied, then the system is said to be memoryless. So what is the given response? H of t is equal to e to the power of t u of -1 minus t. Now you can compare both the expression. So this impulse response is not in this form. That means the given system doesn't possess, that means the given system possess memory, so it is not a memoryless system. So we can conclude like this: since h of t is not in this form, that is not equal to c into delta t, comma, the given system is not memoryless. Okay, so the given system is stable but not a causal system, and it possesses memory, so that's why it is not a memoryless system. Hope you have understood these properties and how we applied these properties to verify whether the given system possess these properties or not. Okay, if you have any queries, do reply or comment in this video. Thank you for your time.